Welcome back, everyone. I hope you enjoyed our module from week 1, where we spent our time doing a quick review of about half of the pre-calculus that we need to have down before we can get started with the calculus. Today we're going to do the other half of that. You'll remember that last week we finished up looking at the generic topic of inverse functions, and the idea was that an inverse function undoes the work of another function. So often if you're solving an equation, whether you think about this or not, you're really doing a bunch of inverse functions. Like if you're solving 4x plus 8 equals 0, you subtract 8 to the other side, but that's really undoing the adding 8 function. Then you divide by 4 or multiply by a quarter. That's undoing the quadrupling function. I know you probably might not think about solving an equation that way, but that really is what you're doing, applying a bunch of inverse functions. So, for example, if we want to solve an equation such as this, 5 times 3 to the x equals 19, we need some way to get this x here by itself. That means we need a way to undo this 3 to the x function. So we need an inverse of the generic exponential function b to the x. And unlike last week where, for example, the inverse of the cubing function was called the cube root function, their names really sound very similar. For historical reasons, which we'll come to in a second, the inverse of an exponential function is actually called logarithm, not called anti-exponential or unexponential or anything like that. So we're going to define this. The log base b of x is the exponent to which we raise b in order to obtain an answer of x. And this, I like to write this all out in words. We've got it written as a formula as well, so you can use whichever you prefer. But this helps me at least remember that it's undoing, that it's reversing, the inverse is reversing the input and the output of the original function. So normally for an exponential function, we get an output. In this case, this x that's being put into the log function is the output of the exponential function. So that was a not very coherent way of saying this. That is y equals log base b of x if we have b raised to the y equals x. In other words, this exponent y is the exponent to which I raise b in order to get x. Okay, you can pause for a second and think about that. I think we've seen logarithmic functions before. And we have a special notation for one logarithmic function in particular, which is when we have the log base e, this special number that we saw last week, 2.71828182845, ... We write that as ln x, and we say natural log of x. Now, at the moment, you might be wondering what's natural about that at all. Why is this number 2.71828, etc., natural? And it shouldn't be clear at all. There's no reason to think at the moment that there's anything natural about that and that it deserves an actual button on your calculator. But it does, and in several weeks from now, we'll have a good idea about why it is natural to want to use this particular exponent. Here's our occasional historical aside. This abbreviation for ln wasn't used until 1893 by a fellow named Irving Stringham. And you might remember that there's another button on your calculator for logs as well, probably. In addition to the ln, there's another base, which is base 10. And another question to ask yourself is, why do we have a log base 10 button on the calculator? Why not log base 7 or log base 13? And you might say, well, the answer is because we use a base 10 number system, and that's true. And the reason that we use a base 10 number system is largely due to the fact that we have 10 fingers, 10 digits. And when you go ahead and you meet the space aliens, I promise you they are not going to have a log base 10 button on their calculator because they're probably not going to have 10 digits on their many hands or whatever it is that they have. So it's mainly an accident of history that we have the log base 10. There's nothing that special about base 10. There is something very special about base e, and as I said, we'll get to that later in the semester. Base 10 is a good number. It does have factors, right? It has factors of 2 and 5, so it's a nice one to use. If we had 12 fingers, it would be much better. If we had a log base 12 button and we did base 12 arithmetic, a lot of calculations would be simpler, like cutting things in thirds or quarters compared to how it is in base 10. And our last little historical note, the original word logarithm, which means ratio number, which sort of makes sense because it's the inverse of the exponential, which is multiplying by a constant ratio, came from our old friend Napier last week, who was also the first one to introduce us to the number 2.71828. And he came up with this name back in 1614. Let's make sure we have a basic idea about how to evaluate some of these. So if we want to evaluate the log base 2 of 32, You can think about that in two ways. One, the log base 2 of 32 should be the exponent to which I raise what? The exponent to which we raise 2 in order to obtain 32. So this is saying 2 raised to what number will give us 32. So you can just try to experiment. 2 to the 1 is 2, 2 to the 2 is 4, 8, 16, 2 to the 5 is 32. So the log base 2 of 32 is 5. Log base 3 of 1/9, that's saying find the exponent to which I raise 3 in order to get 1/9. So here we're saying 3 to the what will give me 1/9. Now we might remember something from last week, that we have a way of writing fractions with exponents by writing something like this. So this is like saying 1 over 3 squared. But we said another way to write that is as 3 to the what from last week by our, I think our second exponent, or maybe our fifth exponent rule from last week, 3 to the negative 2. So this equals negative 2, because if I raise 3 to the negative 2, I get 1/9, like I'm supposed to get here. Here we've got our special base. This is saying natural log. So this is the same as saying the log base e. So it's saying, what do I raise e to get e to the 1,000? And that's almost too easy, you might say. What do I raise e to so that I end up with an answer of e to the 1,000? Well, it's 1,000. E to the 1,000 is e to the 1,000. And it's no surprise that in this case the ln and the e cancel each other out, because the inverse of the exponential function is the log function. So like we talked about last week, if you put something into one of the functions and then put that output into the other, they undo each other just like they're supposed to, and you get right back to where you started. Let's do one last one. Natural log of 0. So that's saying e to the what will give me 0. Remember, e is a number between 2 and 3. So we're saying, what number can I raise a number between 2 and 3 to? To what exponent can I raise that to get 0? Is that possible? And in fact, that's not possible, because we know that the graph of e to the x, like any of our exponential functions from last week, never gets down to the x-axis, right? We have an asymptote. So there is no exponent to which I can raise e. You might be tempted to say something like negative infinity, but negative infinity is not a number. So you've got to pick an actual number. There is no number to which I can raise e to get an answer of 0. So therefore, we have to say that this is undefined. We can only put into the log function things that come out of the exponential function. And as we saw last week, the things that come out of the exponential function are all positive numbers. So we cannot put a 0 into a log function. We cannot put a negative into a log function. But this leads us to our next idea, which is about graphs. We've got a graph of an exponential function here. We'd like to figure out what the graph of its inverse, the log function, looks like. So we've got an applet for you to do to play around with a couple different exponential functions and see how the graphs of their inverses, the log functions, look. Before you actually have the applet draw the inverse for you, I would try to think on your own what it looks like based on what we decided last week about how you get a graph of f inverse once you've already got a graph of f. And then that should help you figure out what the graph of, for example, log base 2 of x should look like from the graph of 2 to the x. So please go ahead and try that applet, and then we'll come back and talk about what you found.